Alright, we could have done this example on the previous lesson, but I thought we'd start it with this just to make sure you're on the right page. Given these two vectors, we want to find the projection of u onto v and then find the vector component of u orthogonal to v. So if I quickly just draw them, just sketch them out. 9, 7 is over 9, up 7. So let's call that 9, 7 with, that's vector u. Vector v is the vector 1, 3. So over 1, up 3. Looks something like that. And you can see if I've made the shadow here going across the projection, so if the sun this time, of course, it's got to be this way, and shadowing it down there, there's going to be, and I'll extend this line, oh, maybe I'll try this. Something like that, and the sun comes down here. You could see this portion right here would be our projection. So the projection of u, and the order does matter, by the way, onto v is equal to, okay, it's the dot product of the two, u dot v over the magnitude squared of, magnitude of v squared times v. And let's not put the dot there, let's times v. Alright, and u dot v, let's take a peek up here. 9 times 1 is 9, plus 7 times 3 is 21. It's going to give me 30 in the numerator. The denominator, the magnitude of v, is the square root of 1 squared plus 3 squared. That expression squared. And then times my vector, and I may put it in component form here. I'll write it as 1, 3. Now remember, this part in parentheses here is a scalar. It tells me what scale, in essence, I'm multiplying this vector by, how long it's going to be. 9 plus 21 is 30. The square root of 10 squared is 10. So I can see that it's going to be 3 times as long as my first vector. Alright, so that final answer is going to be, when I multiply it out, 3, 9. Alright, and to find the vector component of u orthogonal to v, and that's this part right here then, remember we just simply take the vector u minus the one we just found, 3, 9, and it's going to equal W2 if you want to call it that. So this is part A up here. Now we're working on part B. It's a vector. Another one there. And U was the vector 9, 7. Minus 3, 9. And I'm going to just write what that's equal to. 9 minus 3 is 6. And 7 minus 9 is negative 2. And it's not hard to see that you're going over 6 down 2 for that vector as well. So there's my answer. That's the vector component form u orthogonal to v. And I'm going to call that W2. Alright. Our next example is the specific one that we saw earlier. We've got this boat on an inclined plane. Force due to gravity pulls the boat down the ramp and against the ramp. Okay, these two vectors W1 and W2 are orthogonal. They're called the vector components of F. Now first, let's take a peek. What is F? Well, it's a force of coming down. Gravity is pulling straight down. So if I were to put that, I notice that it is 600 pounds, so but it's a negative 600. All right, times, and there's no horizontal movement, so it's simply negative 600J. If I write it in the combination form, it's just negative 600J. All right, what we're looking for then is to find what is W1. What is the projection as I go this way onto this vector right here? Okay, and so if I look at that, I could say, hey, you know, that vector right there is, this one is just parallel to it, right? And this is actually what I'm trying to do. I'm trying to say, how much does it take to keep this from rolling down? So this is a vector that I'm really kind of concerned about. All right, so we want to project F onto this vector V, if you would. All right, and so the vector V, let's figure out, let's call this vector V here. And what is that vector? I notice it's going across. This is a 30-degree angle here. And if I just did the unit vector, which is probably the easiest, I would say I'm going to get vector V is equal to the cosine of 30 degrees I plus the sine of 30 degrees J, excuse me. Okay. And that simplifies, of course, to this cosine of 30 is the square root of 3 over 2 I plus the sine of 30. Oh, excuse me. Let me erase that. And that's 1/2 J. All right, at this time what we're going to do is take the projection then of F onto V, onto this vector V. So I'm going to get that projection. Sorry about the penmanship. Of F onto V is equal to, all right, it's the dot product of these two. So I'm going to get, well, this is really 0 minus 600J, right? So it's 0 times cosine of 30, which is going to be 0, plus negative 600 times 1/2 is going to give me negative 300 over, and the magnitude of V, well, V is, remember, this is a point on the unit circle, right? It's a unit vector. And so the magnitude of that is going to be 1, which is really nice. It saves us some time. And then, of course, we take that times V, which is the vector, if I write it in component form, just the square root of 3 over 2, comma, 1/2. So you see I'm changing forms a little bit just to give you some practice going back and forth from one to the other. Well, this works out simply to be negative 300 times the square root of 3 over 2 times 1/2, and that's a 3 there, folks. There. Okay, so that's its projection. Now, I want to find what is the force required. So what I really want to know is the length, or the magnitude, if you would, of this projection. So what we found right here, this part right here, is that W1 right here. Okay? So what I want to know is, what is its magnitude? How much am I going to need to keep the boat from rolling down? How much force? Okay, an interesting sidelight, by the way, is the steeper this is, of course, the more force I'm going to need. If that's flat, I don't need any force to keep it up there. But is it going to be 600 pounds? Well, to find that, so now I'm simply going to take the magnitude of this, which is the magnitude of this piece as well. So to find the force, it's just the magnitude of this, which is, now here's the nice part, I can actually look at this and say, you know, that's a scalar number and this is a vector. And I could take the magnitude of the scalar times the magnitude of the vector and come up with the same answer. So we're going to break that up. The magnitude of negative 300 is just its absolute value. It's positive, which is 300. And we already discussed earlier that the magnitude of this vector, which is a unit vector, is 1. So I find out my answer is 300. And I've got 300 pounds of force it's going to need to take this. Now you could imagine, well, we could try different angles and you would see, it's going to take more amounts. So I tell you what, I'm going to put a link on here because I've got a worked out example. It's very similar to this. It just has a cart rolling down. So next to this video, I'm going to have a link for another one. In our final example here, before we get to that, we are going to talk about work again. And the work W done by a constant force F as its point of application moves along the vector PQ is given by either of the form W is equal to the magnitude of the projection of F onto PQ times the magnitude of PQ, or simply F dot PQ. Now we're probably going to use this one, I think, quite a bit, and I'll show you something that's pretty nice about this with a specific example if we go back, because we're simply looking at the magnitude here. If we go back to a previous lesson, in fact, let me show you that. Okay, so I went back a few. We're looking here at this part. If I said I want to find the magnitude of this whole thing, and that's the projection, right? If I got to this part and looked and noticed and said, hey, I've got V divided by its magnitude, well, that's a unit vector. Its magnitude is always 1. So if I'm looking for the projection, magnitude of the projection, it's simply the k value, which is the magnitude of the vector u times cosine theta. So a pretty helpful thing. So we're going to try to finish this problem up in a couple minutes. A toy wagon is pulled by exerting a force of 25 pounds on a handle that makes a 20-degree angle with the horizontal. So if I try to draw that again, I'm going to, let's say that's 20 degrees. I know it's more. All right. With the horizontal. Find the work done in pulling the wagon 50 feet. So the distance from here to here is 50. That is the PQ that you saw earlier. So here's my point P, here's my point Q. And then I'm saying I'm going to project this vector down onto that one, right? Well, the amount of work done, it said, was simply the magnitude of the projection of PQ, excuse me, of F onto PQ, so that's an F onto PQ, times the magnitude of PQ. Well, the magnitude of PQ is piece of cake here, that's 50. The projection of F onto PQ, no, sorry for the sloppy writing, is equal to, well, if I go back, I could say, you know, that was simply equal to the magnitude of F times the cosine of the angle, and this angle happens to be 20 degrees, times PQ, which we said was 50. So what is F? Well, that was 25 pounds, so this simply becomes 25 times 50 times the cosine of 20. Really a pretty slick way to do this, so it's worth figuring out all this up. That's 50. All right, so that's 1250 times the cosine of 20 degrees, which is equal to, I did this on my calculator already, it's equal to 1,174.6. And then we're going to label it, since it's a force and we're moving it with pounds on a number of feet, it's in foot-pounds. Kind of a cool little example. Remember, I'm going to give you another example of that rolling down a hill, a cart rolling down a hill, instead of this being a cart being pulled, as well in your videos. So take a peek at that too, please, if you have time.